But for now, I will turn it over to Spiros for the first session.
Hello, can everyone hear me?
Yeah.
Okay. So for this session, it was quite challenging to talk, since I'm also involved in the OpenStack Magnum project for containers, but not including Kubernetes, but I will give it a go. So the main theme is that you have an OpenStack access. Okay, let's start first for me by a few words for me. So work in the CERN Cloud team. I work in the group managed by Tim Bell, which is in the board of directors, and in the same team with Belmiro Moreira, who is in the TC of OpenStack. And inside my team, I mostly focus on container integration with our infrastructure and OpenStack. And I'm a code reviewer in OpenStack Magnum, and I used to be a PTL for a few cycles. So for this session, the main theme is that you have access to an OpenStack private or public cloud, and you want to run some applications in containers, but without using Kubernetes because it's available or it's not an option for any reason. And of course, the other pattern that we see a lot in OpenStack development is the desire to run and manage OpenStack in containers. So before even reaching Kubernetes or any other high-level framework or orchestrator to manage a complicated application such as OpenStack, there are several layers beneath and some complexity that is hidden, or there are also other options that you can use to manage OpenStack or another application like Ansible. So here in this session, we will check why you might not want to run things in containers and how are you going to do that. So starting and the other projects related to running containers on OpenStack. So first we will start from the application, which is like the core component of our architecture, and this will be packaged inside the container image. This all started as a change root in Linux, and then when we talk about container images, we usually talk about tarballs, which are essentially container images, Docker images, and in 2013 that they started being hosted in Docker Hub and being publicly accessible by anyone. So the first question I would like to pose to all of you is which kind of images do you consume? Like if it's an application, everything is built by you. You base you use some base images and you build on top. You just use the base images, because you want to rely to the maintainers of the images like you would do for applications coming from Linux repositories like in Ubuntu or CentOS. And then what do you do for multi-arch? Because even without containers, multi-arch is a challenging task to address, but also, with containers, there is a challenge in building applications for multiple architectures. But once you have streamlined the flow from development to production with containers and all the patterns and tools around it, it should be relatively easy. So usually when you talk about consuming an application like HTTPD or Python or Golang or Apache, you usually go to Docker Hub or another mirror in GCRIO way or your local mirror, and you pull from there. And for example, in OpenStack, Cola and Loki and other images are pushed to Docker Hub and key for users to consume. So I'm not sure, Ashley, now we watch for hands. How do you want to proceed? Can you hear me?
I can.
Okay. And does anyone want to jump in, or we just continue? Um, because this was mostly like a poll of I don't know, interactions. So at least I will start by from our use cases at CERN. So we run different kinds of applications. It could be web apps. We don't run them as cloud team, but our users, which are also our colleagues, run them. Or for us, it's web applications. Well, OpenStack is mainly REST APIs apart from the agents. So usually for unpatched projects that we have, we use the AppStep images that we mirror them. And then if we want to add patches and so on, we rebuild in GitLab CI and push to our registry. So this is also the next bullet point, which is how do you build images? What is the workflow of getting code from development to production? So in our case, we have a private GitLab instance that we host all our code, and we consume heavily the GitLab CI with shared runners that we use across the organization. And for images that we want to build as part of the OpenStack Magnum project, we consume Zool, which is hosted by the OpenStack Foundation. And then for upstream, we push to OpenStack Magnum, which is an organization in Docker Hub. And we have another mirroring key, but recently we don't maintain, since most users are pretty satisfied with Docker Hub, and either they rebuild locally, as we do at CERN, if we want to push some patches or use a tag that has a specific fix that is not upstream yet.
Can I have a question?
Yeah.
So what base images do you use, or you start from scratch?
At CERN, we have also a Linux team that builds some CentOS images that they use Image Factory for this. So for projects that are CERN specific, we use those base images, which is a fork of what the upstream CentOS project is doing. And for the rest of the images that we consume, it's usually, we try to judge what is the official repo that we want to get the image from. Then we mirror a set of tags for this to our GitLab registry. An example is core DNS that we want to run in our Kubernetes clusters. So Docker.io core DNS is like the official image, at least based on the repo. And we mirror selected tags, and then we get always the image from our registry, since we mirrored once every release that they do. Did this answer your question? I lost
yes.
there.
I have a follow-up question, but just stop me if
yeah.
I'm like deriving too much from the topic. So, like, do you have any, let's say, requirements for like a list of bomb switches in the base image of the container, or any requirements to know what is inside, or you just get something from the registry and use it?
So for images that we want to build ourselves, if we won't use our internal from scratch image, we will end up using Debian Slim, which is very minimal, if we want a rich set of packages that are in Debian, or Alpine, if it's relatively easy to build a small image, because usually there is a pattern that you, I'm not talking even for multi-stage builds, but what you can do is have a set of packages that you might want installed in the image, and then build something, for example, a pip install that is going to compile um, some shared libraries, and then uninstall, for example, GCC, you want it to be installed before, and then you want it uninstalled, or some build utils like make. So we either follow that pattern if it's not getting too complicated, and then either we use Debian or the in-house CentOS image, which tends to be a bit fat because you start from 100 and think 60 megabytes uncompressed, and then you start to add things because for YAM and DNF you have already Python there. There is some work to have a slim CentOS with micro DNF, but it's not very widespread, and we don't really use it anywhere.
Do you squash your images, or you have the like install build tools, build and remove build tools in the same command?
No, where it's like it's one build. So what you describe, it's mostly done by the Kubernetes project upstream, that they have 2 Docker files almost everywhere, that they build something and then they commit it, they save it to a tarball, and then they do it from scratch. But this is, it's losing some valuable information from the Docker file. So we tend to craft the layers as good as we can and to have a very small image, because really the benefit from a squashed image is like it's very low, and it's better to have, in my opinion at least, some reference if you do Docker history or Podman history, or with other tools to see the metadata of the image. Otherwise it's lost. You just have a build tag, some labels, if added later, and so on. Also, yeah, I didn't mention that for Golang projects, everything is from scratch there, of course, and with Cgo disabled to have it working like everywhere with a very small size. Do you have another question, or anyone else? I see some input from John and Fanji in the relative bullet for how do you build your images.
Hey,
in the build your own, yeah, tell me.
Oh, sorry. I was just going to say, I was going to share what we were doing with building our own color images, because you did mention the color project.
Yeah.
And I'm curious what other people do. What color generally does is it actually builds up its own custom images, and they're generally using OS packages effectively. So say you take the CentOS or Ubuntu base or whatever, and it builds up from that. And I guess, as you mentioned earlier, they can be a bit fat, but sometimes that's a benefit when you're debugging. Bash is definitely there, for example. Whether that's an anti-pattern or not is probably an interesting question. And yeah, that's
so yeah. So for applications like this, even for OpenStack, we start with images that are, to answer your question, not exactly validated that everything is working, but then everything gets deployed first, like the binaries, if are there or not. So the binaries are first in, the images first are tested to isolated testing environment. In our cases, at least for Magnum and the other OpenStack projects, we have like a testing region plus a dedicated testing deployment. So everything gets validated there, and then images with the same SHA will end up in production. And for going from fat images to like slim ones, usually you start with a fat image, you are getting comfortable, and then you go slimmer. And then there are other patterns you can do to debug images, like either access the host or run a very privileged container next to it in the same namespace, or attach with Kubernetes or Docker a container just next to it and do debugging there. But this is like if you have a very fine-tuned environment and you don't want to disrupt anything, these patterns are useful there. But if you have capacity, a fat image can make your life easier.
I mean, maybe if no one else has got questions, I'm curious how you put your containers on a diet. Like what approach you took to do that.
So putting a container on a diet is you must know the application very well and be sure what are the exact requirements. And if you're using a repository like Yum or apt, you must know very well how to use the package manager. A very common advice for apt is apt get install minus no recommends. Do not install additional packages. In some cases, you might even get tech, which will explode the size. And for CentOS, you can add a flag to never install documentation, because inside the container, man pages is not something that you need. Also clearing any cache that you have in varlib apt or in varlib yum. You don't need it while you run, because ideally you should never install something in the container. And based on what you're using, you can make even the file system of the container read-only. So the cache, you will not need it anyway. Another pattern is what I mentioned before, that you have like a very long run command or a script that is executed in the run statement in a Docker file that will first install some regex. It will install the application and then will remove whatever it doesn't need. So make or auto make, you definitely don't need when you're under your application. Well, if you need it, it's a very different story. Your application is very specific. So these are the main goals. And then for Golang, of course, and Rust, multi-stage builds is the holy grail, because it's impossible to get lower than that. It's absolute the slimmest.
And real quick, we actually just teed up a poll just to get a sense from the folks that are attending on who's running containers in production, or if you're just planning to and evaluating that implementation. So I think we're going to run a poll, Spiros, while the discussion goes on, just to kind of see what kind of content would be helpful for those folks. So I think we're going to push that live now. There we go. So please vote in the poll, and then we'll try to customize the conversation based on the responses. Thanks.
Well, it seems that the production containers have reached production, at least as we can see, but let's wait a bit more. So to continue, so one of the first things that is important for using OpenStack and containers is make sure that all the infrastructure behind it, like the registry and all the CI, is there. And then OpenStack provides like a great set of APIs, like the Nova API, storage APIs like Cinder, Manila, and Swift, and of course Neutron. That at some point this becomes invisible. So when we run, in our case at CERN, VMs, it's very fast to boot, and I think for bare metal, it's as fast as possible. It cannot get close to VMs, the speed of booting new servers, but at least it's very good. And all this scaling up sets of VMs, like either Kubernetes clusters or not, or pools of VMs, it's very fast. And with declarative deployment, even with Ansible or Puppet, you can scale like horizontally in many cases, and not thinking of the infrastructure, the OpenStack infrastructure underneath, because if it's streamlined enough, you don't even see it or think about it. So it seems that half of the people at least are using containers in production, which is great. And I think improvements in all the request, the infrastructure is very important. So even for people that run containers in production, there are new projects like that like the one that we started using recently, which is Go Harbor, which is a registry, an OCI registry, a compliant OCI registry for Helm charts and containers. And of course, there is GitLab and Nexus, but all of these are as good as, I didn't know even for the registry. This must be new even for me. But all of these projects are as good as their backend. So if you're running containers in production at a certain scale, distribution is very important. So all of these projects support S3. That could be Swift or something else. In our case, is Rados Gateway, but it's hidden or it's, let's say, included in the OpenStack catalog that users can consume with OpenStack or the AWS credentials that OpenStack provides. And then very close to it, what's very important for, especially for production workloads that we struggle very hard to put in place at CERN, but it's very, very important coming from a world from signed packages with GPG keys, is image signing and allowing only images signed by a specific CI. And then image scans, because you might have a container running for a long time and at the same time CVs are discovered. But if you follow the pattern with read-only, you need to constantly to monitor it and update it. If you're running in a, let's say, older system that runs Ubuntu or CentOS, you can do updates and get the latest packages from the respective registry, from the respective package repository. And also this is a challenge for while building, and even projects like the OpenStack Kubernetes SIG that it's in 2 sessions after today. We don't have their implemented signing of the packages. We just release the tarbles and the binaries, and we post them in the release page of GitHub, and in other cases. For the images, we just push the image there. So the goal is to reach a level as what we have for the release artifacts of OpenStack, which is in tarbles.openstack.org, that the tarbles are signed and you can verify what you download from there. Projects like Harbor that I mentioned, or I haven't checked the state on Zool, but GitLab as well, they offer, they can host images signed because the signature is part of the manifest, but all the tooling and managing the private keys is up to the operator. So this is a challenge, and it's not very well documented or solved, I would say. Has anyone solved this or has any suggestions? Because what I can offer on the table on the discussion is that we, if it's GitHub, we store the secret in GitHub. If it's Zool and Jerrit for OpenStack, we have the key in the Git repo encrypted with the public key of Zool and pushed to the Zool file, zool.yaml or in their directory. And for GitLab, it's the same. You can have variables that are protected and you can store them in GitLab. And then the CI will just use the secret. I think the optimal one for now, at least from my input, is Zool, that you can encrypt, that you have a master key that encrypts with the public key all the other secrets in, and you can host it in Git entry. Anything you want to add on this, or we can move on, go a bit faster to next topics, going away from images. Okay, so let's move on to how do you run containers. So in the realm where you have the Kubernetes cluster, this will be hidden from you, but there is something that will run your container for you. So it will download the image, unpack it, and create the change root and the namespace, and it will start the container, attach it to a daemon or systemd or something else. So the most popular, I think, at least even now, is Docker, and containerd is very close, even if it's already used by Docker. And if you're in the RHEL-like distribution, Podman is definitely there for at least lightweight containers. Kata containers are already in with lightweight virtualization, which is extremely useful if you want to have multi-tenancy in hosts that are consumed by different tenants, and especially if these tenants don't trust each other. So if you run Docker Swarm cluster, but is used only by one person with the Swarm API, it's fine to not have a very high degree of isolation. But if this Swarm cluster or a set of hosts that run Docker engine is part of a CI, the code that runs there isn't trusted, the network might also host sensitive applications, and you want to be extra cautious there. And Kata containers there help a lot. gvisor is also another option, which shares similar semantics, or Rust VMM that has recently been published. But at least the most popular for now runtime is Docker, I think, and containerd, and Podman is used with the systemd pattern that you run Podman inside a systemd unit. And this is at least what we do in the OpenStack Magnum project, and I think also the Typhoon Poseidon project is doing to run Kubernetes itself. So the kubelet runs in a Podman container, and you can push it even further, that even run containerd inside the container, because it will you will do all the appropriate bind mounts, and it will talk to run C on the host. Do you have any questions on that, on runtimes, or if you want to discuss something there? I see that the OpenStack collaborator is using Docker and Docker Compose. Okay, I see some action in the Etherpad, so we'll wait for some more input. Okay, there are some comments about the differences in Podman and Docker. It's not exactly the same. Yeah, of course. The goal is to mimic the API, but the Docker API, but if you have like special requirements, it might not be so easy. Unless ping in the Zoom chat, let's move to the next subject. So I think I see John that mentions what do you need from OpenStack to run your containers. Well, we definitely need compute to run the containers, but then these containers do not be just black busy boxes. You need networking and storage that they have two bullets after, which means storage is used either to share some state or to store some state. So storage could be block storage or S3 or a shared file system, even SFS or NFS, or something similar. And then this is where OpenStack offers the great abstraction with its APIs that you can, well, and other clouds as well, of course, that you can interact with storage, and everything will be in code. You can test it in the CI, and so on. So this is even true for running OpenStack. Thankfully, in most OpenStack projects, the state is only MySQL. Well, only MySQL is not that easy to run, but it's a very well-known and established technology. But either you run it with Ansible or just Puppet, or on Kubernetes with plain manifests or OpenStack Helm. The most important part is the networking that you need to achieve, but Kubernetes has already a very complicated stack for that. But since in this discussion we're excluding this, what is very important is, well, not very important, the most important benefit from running in containers is the reproducible environment, that if you have built an image based on Ubuntu or CentOS, you can run it anywhere you want and it will behave in the same pattern, at least for OpenStack, which is just quoted REST APIs for the control plane. And so this is extremely useful and easy to consume. Then if you're going to move to how all these microservices will interact with each other and what to do with networking, avoiding Kubernetes, the go-to solution is some proxy in front, and a lot of business logic will be in the either HA proxy or Nginx configuration, which will involve the virtual IP, which will involve also virtual IPs or DNS host name in the same IP, and path-based routing that even in DevStack, we use this pattern for all the projects in the catalog. Instead of ports and different IPs, we just use the path of the URI. Do you want to comment, or is anyone running, let's say, OpenStack in containers other than Kubernetes? Ansible is a very popular option, and TripleO recently.
I'm certainly a +1 for Ansible.
Okay.
So I can share. I guess it goes back to your point on reproducibility. So, I mean, we obviously work quite a lot in the HPC science space, and reproducibility is a big thing for our users. But not only that, this clearly obviously helps for OpenStack. It's really nice to know that the exact same binary that you executed in your test environment is the one that you're moving to production. And that simplicity is so powerful, I think. And Ansible certainly brings that to the whole stack. As I said, the Collar containers are, built in their way.
And apart from reproducibility is, of course, isolation done with features of the Linux kernel. And you can use control groups for not having. Keystone is one of the services that can be attacked first. And for example, number of connections there could be limited even per backend if we assume the front end is a proxy, or the size in memory or the CPU consumed by Keystone. You can always try to confine it in smaller space in your host and not affect other services, or even for bags. if you have a bug in, let's say, in heat, and it starts exploding number of connections or in memory, with these limits and features from the Linux kernel, you can achieve some isolation. Or if a service is compromised, you can still get away with the isolation that the container interface, it's not exactly interface, but pattern gives you.
I would say one of the big things I think I've seen moving to working with all containerized deployments, having previously worked in an awful lot of VM-based deployments, is actually the lack of isolation is also a benefit. So I should justify that slightly. What I mean by is we can put C group limits on all of the containers, but they can all share a certain amount of wiggle room, let's say. So if one of them does go crazy, you've got a bit of time knowing it's going crazy before it's going to hit the brick wall. So you can kind of go in there, take evasive action, fix it without actually hitting a hard limit, which you tend to hit in the VM world because you're effectively dedicating RAM for each of your components. So you have got a bit more flexibility with the container approach, which is very attractive when you're trying to, well, just operate the system really.
Yep, definitely. Well, that's an excellent point, because you need, as you said, isolation, but also some flexibility, because you never know, you cannot always pre-allocate the resources.
And you said about isolation, I guess one of the key isolations is the version isolation. So if we just did, say, on one system packages for all of the components for OpenStack, this is a fairly common example, right? It can be a bit of a nightmare to say, oh, Spiros has added this great new feature in Magnum, so I want to upgrade Magnum before everything else, which we've totally done. That's possible with containers in the sense that you can just, if the service dependencies are fine, you move it forward without even thinking twice about the package dependencies, because they're independent for each of your container images, which I'm sure hits most.
I think there is very important all the path from development to production. It's easier to create it with containers than with RPMs or packages, because you have to set up repos, and there's quite some infrastructure around it. Because, okay, we mentioned all these benefits as for versions, but also with VMs we had achieved that before. But like the next iteration is with images, that the development flow can be streamlined more. That can be good and bad, because you have some flexibility and ease of use, but also it can be skewed, and you can get into paths that you don't control it very well, or it's a bit loose, the procedures for getting to from one version to another. I think I already discussed. Is there another point that anyone wants to raise about it, or we can, because I think we have around 10 minutes more or 15 to talk a bit about storage and networking. It's not much to say, because if OpenStack works very well, you have Octavia as well there in Neutron, maybe the networking problem is kind of solved. Okay, let's start from storage. I mentioned that the storage requirements might be different per application. You might need block storage, you might need shared storage, or just something to archive results like S3. So for Kubernetes, we have the CSI interface, the container storage interface, that there was at some point, I think, an attempt, and that CSI is there not only for Kubernetes. But even without it, we have the Docker plugins that Cinder as well has at least one plugin. I think it has two. One is part of Rexray and one is part of Fuxi. And the other option is to never have a state or something that you access via POSIX to your containers. So you do all the management of storage disentangled from the runtime. So if you have some hosts that you can have a container technology deployed inside, you can mount everything you need. And then you bind mount the directories, which are essentially mount points to your container to access it. This can be NFS, it can be Cinder volumes, CFFS with carved by Manila, or anything really. But I think in the cloud era, having an API there as well is a major benefit. Like if you have S3, you can do snapshots of your work, but the logic will be embedded in the application, or you can do immutable writes and let's say atomic writes to S3, because if you use name tags that have a timestamp inside or a signature, the operation to S3 will be atomic, an HTTP post, and you will get the status code, and then you can try again or not. This is not exactly read-write many, it's read-write once, but the application doesn't need read-write many in this sense, because you have read-write once per file. It's read-write many for different files. So if each instance needs to write or read different files, S3 can be read-write many in a way. So yeah, I would be, say for myself, a great advocate of this pattern running with an S3 API. It would be Swift, Minio, or something else. But of course, the POSIX access is still relevant to many use cases. So if anyone else wants to add something there, what is the preferred pattern? Not sure if we can are fast enough to run another poll, but if you want, you can just jump in and leave a comment or just open your mic.
So one of the challenges I think I've seen people struggle with is the fact there's all of these options and it's not entirely clear which is a great one to use for the particular use case, or not immediately clear. I don't know. So I've tried, I see there's some people adding notes actually. I tried to sort of write out the various ways you can attach storage with an OpenStack in the different use cases, just to try and capture what you're saying. So definitely there's the ephemeral local disk. And I know you mentioned MySQL. Like one of the things databases kind of like is low latency, right? And one of the easiest ways to do that is that you're using the local hypervisor disk. That's all good. The disadvantage is, in order to get a bigger one, you need to change your flavor size. So you kind of need to have predicted in advance what size flavor that VM, or in that fact bare metal, has by default. Which is where Cinder can be useful if you don't really know how much storage you need in advance, but it's the same kind of read-write once thing, but at least you've got that flexibility that as your, and actually as your pod moves, you can reconnect the volume in the different places. Although I'm going on to a topic we weren't going to mention. But yeah, I guess, and the Manila is very useful for exactly the, maybe the person in red wants to comment. Don't know who that is.
I think it's Tom.
Maybe that's Tom, yeah.
Yeah, that was me.
We've definitely used the goodness of Manila, but maybe you want to summarize.
Well, I just tried to put down two of the reasons that I think Manila, kind of shines in a world with containers. One is that because it serves storage over a network and is not tightly coupled with Nova, it doesn't really care whether the consumer are bare metal or VMs or containers hosted on bare metal or VMs. And indeed, they can even span these groups of things. So there are some use cases where that's quite useful. We actually have some customers who are prototyping with that right now. And then the other is that it does what, at least in Kubernetes terms, is called read-write many, or RWX, but basically multiple writers, multiple concurrent writers with POSIX file system write arbitration. So you will note that, I'll note that read-write many is also possible with Sender today in raw block mode, which is a new thing. Where you access the block device as a block device and use file offsets to it and arbitrate writes via the application. So, you know, for example, a database that works with raw block, but it's typically one application. It's not traditional Kubernetes, at least. I know we're talking about other container orchestrators here, but that's what I'm most familiar with, where a node local file system is applied right away. So for instance, Sender multi-attach, I've worked on Sender more than I worked on Manila in my life, is useful if you have a cluster file system. And I don't know about all the container orchestrators, but Kubernetes does not have one. It imposes a node local file system if you put a file system on it. So it's not safe. So Manila is actually quite useful here, and its lack of tight coupling with Nova, which might have been a disadvantage in the traditional OpenStack world, actually turns out to be a bit of an advantage in this new world order, as it were. Obviously, I can talk about this at some length. I'll refrain right now, but you folks know who I am. I'm interested in the subject.
Do you see NFS as an option?
Right now, Manila works through the cloud provider OpenStack. I know Anusha Ramyani will be here later talking about that with CSI provider. And the CSI provider currently works with Manila with NFS and with Manila with native CephFS. Manila is a multi-protocol abstraction, you know, control plane abstraction for OpenStack. You know, upstream there's HDFS and CIFS and all kinds of stuff. But the two live ones currently here are NFS and native CephFS. Does that answer your question, Prakash, or not?
Yeah, thanks. Yeah, that helps.
So for NFS, you know, I work for Red Hat, and we're putting this is in production. So, you know, I'd love to see it in production with other distributions and so on, and as well. But with OpenShift, it's currently running with NFS, and CephFS is queued up, but CephFS works fine upstream, and the CERN guys, I think, are starting to play with it with CSI. Maybe they're further along. They were already using the non-CSI provisioner for Manila with CephFS very, very successfully.
Yep, I can definitely agree to that. We did, and we're moving gradually to Manila CSI. So I think we have about 1 or 2 minutes. So thanks for the discussion, at least for storage, John and Tom. Just to wrap up, I would like to mention that all the infrastructure and all the projects around it for the CI image distribution and the different runtimes, different plugins to access and to access storage are crucial. And even if you use a big orchestrator like Kubernetes or anything else. And there are a lot of optimizations that can be done to achieve a great performance and a declarative way of deployment. I have also left some notes, 2 more points underneath, which is a subject, one of the subjects that we work at CERN recently, which is image distribution, because the registry can be a single point of failure of the application depending on the backend. And of course, caching and then architecture of the image distribution is very important. And what I wanted to touch slightly, because in all this discussion we assumed Windows, Linux as the host, Windows containers are kind of a thing, and a large portion of the industry is based on that, but I don't think we have time today. So yeah, just to wrap up again, there's a lot of projects outside Kubernetes and Docker and the main ones, even for monitoring that we didn't touch today, like Prometheus, Grafana, and all the various plugins and exporters you can have for containers are extremely important. So thanks everyone for joining the discussion. I think Ashley will jump in, or someone else from the foundation. So I think that's everything from me. So thank you.
Thanks so much. That was great.